Hello everyone. Today we're going to talk about the rational roots test. We use the rational roots test in order to find possible roots, the zeros of a polynomial, to serve as a guide for synthetic division factoring. That way we're not just plugging in random numbers, we're actually working from a pool of numbers. And this pool of numbers are going to be based off of our leading coefficient, which will become our denominator of our pool, and our constant term, which will become the numerator of our pool. Specifically, we're looking at the factors of the leading coefficient and of the constant term, setting them up in a ratio, such as P over Q. Removing any duplicates, then from that pool, we have the potential numbers to work with. So, let's take a look at some guided practice. And this will be a really short video. Our leading coefficient here is the value 1. The factors of 1 are plus or minus 1. So setting up our fractional bar, plus or minus 1, goes into our denominator. Meanwhile, our constant is 3. What are the factors of 3? Well, plus or minus 1 and plus or minus 3, which produce a pool of numbers for us to work with, such as 1, 3, -1, and -3, such that when we go to do our synthetic division, we're going to check against this pool. So let's check the value 1, x equals 1. So 1 on the outside, make a little box, coefficients of 1, 1, -5, and 3. 1 comes down. 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. 2 plus -5, -3. -3 times 1, -3 plus 3, 0. So remainder 0, which means that 1 is a proper root. Now that we've found one proper root, we don't need to go back to this original function in order to test the other ones. We can actually use these coefficients to test this, because these coefficients here are actually part of our same original function, except now we have x squared plus 2x minus 3, and all that's being multiplied by what we factored out, x minus 1. So we're going to use these coefficients to check against our 3, our minus 1, and our minus 3. So let's check our 3. 3 on the outside, coefficients of 1, 2, -3. The 1 comes down. 3 times 1 is 3, plus 2 is 5, times 3, 15, plus -3 gives us 12. 12 is not 0, so x equals 3 is not going to be a valid root for us. Let's check our minus 1. Have our coefficients, 1, 2, -3. 1 comes down. 1 times -1, -1. -1 plus 2 is 1. -1 times 1 gives us -1. -1 plus -3 gives us -4. -4 is not 0, so -1 does not work as a root. Let's check that minus 3. We have our -3. We have our 1, our 2, and our -3. The 1 comes down. 1 times -3, -3. -3 plus 2, -1. -1 times -3, 3. 3 plus -3, 0. Remainder 0. So -3 is a root. So far, folks, we have found that we can factor out this original function of x cubed plus x squared minus 5x plus 3 as an x minus 1, as an x plus 3. Then we're left with this down here. Well, this here, this is our constant. This is our coefficient, our x value. That down there is just another x minus 1. So this function here can simplify to x minus 1 times x plus 3 times x minus 1. Or, if you want to make it even simpler, x minus 1 squared times x plus 3. Let's look at another one. This time we're missing some zeros, and that's okay, because as we need to do for synthetic division, we're going to put them back in. So this equation is really the same as x cubed plus 0x squared plus 0x minus 27. Our leading coefficient is 1, plus or minus. Our constant, we got a negative 27. So factors of that are going to be plus or minus 1, plus or minus 27, plus or minus 3, plus or minus 9, which will in turn give us a pool of numbers to work from, such as 1, 3, 9, 27, negative 1, negative 3, negative 9, negative 27. Now, I don't really want to work with these positive 27, negative 27 if I don't have to, so we're going to start off with these smaller values first. Let's check positive 1. So we have our 1 on the outside, and then we have our coefficients of 1, 0, 0, minus 27. 1 comes down for 1. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1 for negative 26, which is not a 0. So 1 does not work as a 0. Next we can try minus 1. Testing our minus 1 against this. We have 1, 0, 0, negative 27. We have, the 1 comes down. 1 times negative 1, negative 1, plus 0, negative 1. Negative 1 times negative 1 is 1. Plus 0 is 1, times 1 is negative 1. Plus that is negative 28. Also not a 0. Done with that. Let's check the 3 then. Let's go with positive 3. 1, 0, 0, minus 27. Well, the 1 comes down. 1 times 3 is 3, plus 0 is 3. 3 times 3 is 9, plus 0 is 9. 3 times 9 is 27, plus negative 27, 0. So 3 is actually a root. And then if we keep going, if we check the rest of these, negative 3, 9, minus 9, 27, negative 27, we're not going to end up with roots. The only root from this pool that is true is x equals 3. But this equation here, this x cubed minus 27, it's not going to be the same. Let's see, x cubed minus 27 is not the same thing as simply saying x minus 3 cubed, okay? What this actually is, and some of you might have picked up on it from Algebra 2, this is actually known as the difference of cubes. That is to say that some value cubed minus another value cubed is equal to the cubic root in this case our minus 3, times another trinomial. And I'll put a review video in the previous courses folder for this. Functionally, applying our difference of cubes formula would mean that this would be rewritten as, let's see, x cubed minus 27 would be equal to x minus 3 times x squared plus 3x plus 9 as our two factors. And as you may recall from imaginary numbers, this is probably going to have some imaginary roots, okay? So using our pool, our rational roots test, we came up with this giant pool. From this, the only number that actually works is x equals 3, meaning that x minus 3 is a factor of the original problem. All we're doing today, folks, are notes on this. We'll have an assignment on this tomorrow. Reminder, you have a test over polynomials and synthetic division next Monday.